The Central Processing Unit, or CPU, is the heart of any computer system. It executes instructions from software, controlling everything from basic calculations to complex graphical rendering. A powerful CPU ensures smooth multitasking, faster application loading, and an overall enhanced computing experience. Understanding the factors that influence CPU performance is crucial for making informed decisions when building or upgrading a computer system. One of the most fundamental factors is CPU clock speed, measured in gigahertz, (GHz). Clock speed refers to the number of instructions a CPU can process per second. Higher clock speeds generally translate to faster processing. However, there are limitations. Higher clock speeds generate more heat, requiring robust cooling solutions. Another important factor is the number of cores in a CPU. Each core acts as an individual processing unit, allowing the CPU to handle multiple tasks concurrently. This parallel processing capability is particularly beneficial for multitasking and demanding applications like video editing and gaming. However, software must be optimized to take advantage of multiple cores, otherwise the additional cores may not be fully utilized. CPU architecture plays a crucial role in performance. Modern architectures incorporate advanced features such as branch prediction and out-of-order execution to improve efficiency. These features enable the CPU to anticipate future instructions and execute them in a more efficient order, resulting in significant performance gains. While the CPU is a critical component, it doesn't operate in isolation. The amount and speed of RAM significantly impact system performance. RAM, or random access memory, stores data that the CPU needs to access quickly. Having sufficient RAM prevents the CPU from constantly accessing the hard drive, which is a much slower process. Moreover, faster RAM speeds allow for quicker data transfer between the CPU and memory, further enhancing performance. Storage type and speed also play a role. Solid-state drives, SSDs, have become increasingly popular due to their significantly faster read and write speeds compared to traditional hard disk drives, HDDs. SSDs use flash memory, enabling much faster data access, resulting in quicker boot times, faster application loading, and overall snappier system responsiveness. While the CPU is the primary processing unit, the graphics processing unit, GPU, plays a vital role in handling graphics-intensive tasks. GPUs are specifically designed for parallel processing and excel at handling complex graphical computations. They offload the CPU, freeing it to handle other tasks. To maximize CPU performance, achieving a balance between these factors is essential. For instance, a high clock speed CPU with insufficient RAM would be bottlenecked by the slow data transfer rates. Similarly, a powerful GPU would be underutilized if paired with a weak CPU. Pipelining is a technique employed in CPUs to improve performance by overlapping the execution of multiple instructions. It's akin to an assembly line, where different stages of instruction processing occur simultaneously. This parallelization of tasks significantly increases the throughput of the CPU. Each stage in the pipeline handles a specific part of the instruction cycle, such as fetching the instruction, decoding it, executing the operation, and writing the result back to memory. The CPU cache is a small, high-speed memory located directly on the CPU chip. It stores frequently accessed data and instructions, allowing the CPU to retrieve them much faster than from the main memory. The CPU cache is organized into levels, with Level 1, L1 cache being the smallest and fastest, followed by Level 2, L2, and Level 3, L3 caches. When the CPU needs to access a piece of data, it first checks the L1 cache. If the data is found, it's called a cache hit. If not, the CPU will check the L2 and L3 caches, and finally, the main memory. Cache hits significantly speed up processing, as accessing data from the cache is much faster than accessing it from the main memory. Virtual memory is a memory management technique that allows a computer to compensate for physical memory limitations. It uses a portion of the hard drive to simulate additional RAM. When the system runs low on physical memory, it can swap data between RAM and the virtual memory on the hard drive. This process allows the system to run more applications and handle larger data sets than would be possible with physical memory alone. Understanding the interplay of these factors is essential for building and maintaining a high-performance computer system. By carefully considering these aspects and striving for a balance, users can ensure their systems operate at their full potential.